I'll make us live on YouTube. Right, 5, 4, 3, 2, 1.
Good evening, everyone. Welcome to the Geological Society's virtual public lecture, Adventures in Martian Deep Time. Tales from the Perseverance Rover. This is going to be presented by my good friend and colleague, Professor Sanjeev Gupta of Imperial College. So, hello, Sanjeev. My name is Matt Baum. I'm a professor of planetary geoscience at Open University, and like Sanjeev, I study the geology of Mars. Now, I'm not going to give a big intro. Sanjeev's got an awful lot of amazing pictures to get through, so he's asked me to keep this short so we can get on with the lecture. But first, I do have to give some important information. So first of all, during the lecture, all audience microphones will be muted, and so will all the video cameras. You'll only be able to hear and see the speakers, but there will be a 15-minute question and answer session at the end of Sanjeev's presentation. So if you could submit questions using the Q&A box function, we can look at those and then send those back to Sanjeev at the end. We may not be able to get through all of the questions submitted, but we will do our best. Finally, this video will be live streamed, recorded onto YouTube, and then it will be uploaded onto the Geological Society's channel. So without further ado, straight over to you, Sanjeev.
Thanks, Matt. God, it's a bit terrifying being live streamed on YouTube. Maybe only 5 people are watching, I hope. Okay, so thanks everyone for joining in. Welcome to Mars. It's certainly not as warm on Mars as it is here in London. It's actually amazing weather. I'm tempted to pop out to the park now. I will maybe later. So what I want to do is, I'm incredibly privileged, actually. I'm a terrestrial geologist who's got involved with Mars research, and I'm terribly privileged to have the chance to actually work on 2 Mars rovers. There's 3 Mars rovers at the moment. The old rover, Curiosity, still doing amazing science, Perseverance, and obviously the new Chinese rover, Zhurong. And I work on both Curiosity and Perseverance, and it's just an amazing opportunity. So what I want to do is really talk about the early adventures of Perseverance, give you a bit of background to the mission, etc. And then I have way too many slides, so I'll zip through, because actually the timing of this talk is absolutely perfect, because in the last week, Perseverance has done something really amazing. And we've got lots and lots of images, so it's great to be able to talk about. And obviously, you know, what's really great is I work with the Perseverance science team and engineering team. So the science team is actually almost 400 scientists, so it's an incredible team, and 200 engineers who make all of the science we want possible. And that's just an extraordinary engineering feat that they're able to do. So what are we interested in? So this is arguably the most famous geological outcrop in the world, Siccar Point in Scotland, where James Hutton introduced that concept of deep time. And we have generally a pretty good understanding of deep time on Earth. And what we're doing is, through the rock record, sedimentary rocks are our archive into past. It's the only way we can reconstruct what past environments and climates were like. And we do this through analyzing the rock record. And we're beginning that journey on another planet now. And we've had a bunch of landers and rovers investigating Mars. And then it's really these 2 laboratory systems, rovers, Curiosity and Perseverance, that are changing game. And Perseverance does something very new that really is radically different to what Curiosity has done. So firstly, today, modern Mars, I won't say it's boring, because Matt would probably kill me, but modern Mars is hyper arid and hyper cold. There's no running liquid water at the surface because liquid water is not stable. And so it's a very barren, harsh environment, not suitable for life. But we send rover missions to Mars really to search for life. And we're not looking for, in general, not looking for present-day life, because it's thought that present-day life potentially is present-day life, but it's likely that it's too hard. The conditions are too harsh for present-day life. But it's thought that Mars, 3.7 to 3.6 billion years ago, had a much warmer and wetter climate, and we see evidence from orbital observations of river channels, valley networks, ancient evidence for ancient paleo lake systems in craters. And there's even suggestions that in the northern lowlands of Mars, we had an ancient ocean. That's a hotly disputed problem, and we haven't resolved that. But ancient Mars is thought to have been habitable. But what we really need, as all geologists will attest, is we need actually to be able to look at the rocks and look at them and interrogate them in detail to reconstruct that history of Mars's evolution in detail. And really, I would say actually, not just the search for life. I mean, we're going to rocks that on Earth are the rocks that are the same age as rocks on Earth that have the earliest life on Earth. But another reason to really go to Mars is that that earliest record of Earth's history has been erased due to plate tectonics. So we don't preserve that. And so Mars does not have plate tectonic cycles. So Mars has abundant rocks at its surface that are very, very old. And so it's a way of getting a window into the early evolution of terrestrial planets that can enhance our own understanding of Earth. So where did Perseverance land? Perseverance landed over here, and those of you who are familiar with the movie The Martian, this is where this character landed and is probably still there given some of the things he's talked about subsequently. Turning to the mission objectives for Perseverance. So firstly, it's geologic exploration. It's to explore an ancient environment on Mars and understand the process of formation and alteration. Obviously, it's to look for the habitability. Was that environment suitable for life? In our Earth-centric view, that's what we go with. And also to seek evidence for past life. Obviously, we'd love to discover some dinosaur bones or something like that. Obviously, we're not going to discover dinosaur bones, but we're looking for telltale signatures in the rocks that might hint at a life, potentially. And then the most important part of the mission is to prepare what we call a returnable cache. So it's to collect samples, core samples, up to 40, and leave them on the surface of Mars for future missions to return to Earth. And that's the prime motivation for the mission, is to get rocks from Mars back to Earth, because that's really where it will be game-changing. I think most scientists think that it's going to be pretty difficult to discover life on Mars with a rover, with the instruments on a rover. But I think once you can interrogate those cores in Earth laboratories, in terms of the chemistry and the chemical signatures of life, will have a much better chance. And finally, it is also has instruments to prepare for human exploration. So we've got a weather station on board, which is measuring the temperature, humidity, wind and dust environment. So that helps us understand the environment that astronauts will experience on Mars. And one of the big instruments on the mission is called MOXIE, which is basically demonstrating in situ resource development. So obviously we need oxygen for astronauts to breathe and for rocket fuel. So it's testing techniques to convert atmospheric CO2 into oxygen. Okay, and obviously, this is the sort of signature that we would love to have. These are microbial stromatolites from Australia, 3.5 billion years old. We would love to discover something like this. Who knows what the chances are, but even small scale signatures of microbial life would be fantastic, but it's more likely that we would have chemical signatures in the rocks. Okay, and I'm not going to talk about Curiosity. Even though I work on Curiosity, I feel really bad about not talking about Curiosity, because Curiosity is doing amazing things. And I just wanted to show this because Curiosity drilled its 33rd drill sample just a few days ago. And this is actually, the drill target has been named after a very famous Scottish geologist, whose name is promptly Maria Gordon, who is one of the first female fellows of the Geological Society of London. So it's amazing we've named this after her. And this rock sample is going to be really exciting because we're getting into a new unit, which orbital signatures tell us have a sulfate signature. So we're really interested in what these rocks tell us. Okay, so this is Perseverance, and we have a whole host of instruments on board, and which I'll talk about. I won't talk about all the instruments because there's so many of them. But first up, we have the Mastcam cameras. Z cameras. I'm on the Mastcam Z team, and these are zoomable, multispectral, stereoscopic cameras and produce high definition video. These are the cameras that produce the beautiful mosaics that you see. And stereoscopic views of Mars. There are eyes of the rover, basically. Next to them, we also have the nav cameras, the engineering cameras, and those are the most important, if you like, of the instruments, because they allow us to first see the landscape, and that's what the rover drivers, what we call the rover planners, use to plan drive paths for things. Above that, we have SuperCam, which is a laser. This is it being built over here. Does remote optical measurements and laser spectroscopy to do the fine scale mineralogy chemistry of rocks. We use it for range finding chemistry. And then we have one of the instruments is Sherlock, which does scanning Raman and luminescence organics and chemicals, so deep UV resonance Raman. And we have a whole bunch of other instruments that I won't talk about. Okay, and then most importantly, at the end of the arm, we have the turret over here, which has two of the instruments, Sherlock and Pixel, but also has the whole drill assembly system, which is what's coring the samples that we will return to Earth. So this just shows you the turret over here. This is the drill assembly. So these are the stabilizers over here, and this is the drill thing here. So very, very complex thing. And these are all our abrading bits and our coring bits over here. And this is to collect regolith samples. And there's tons of information on the Perseverance website. So please go and check out that in terms of the detail. And inside the rover, this is the sample cache assembly system. And this is where the tubes, the samples, are in titanium tubes. And this is where they're stored, basically, as the rover is driving. So we're going to be collecting cores, putting them into this, imaging them with a cache cam. We have this is the sample handling arm. And then eventually they will be deposited on the surface of Mars at a depot where they can be collected by a future mission. So I'll talk about that a little bit later. Okay, again, Jezero context. This is a molar map of Mars. This is where all the other missions have landed. I don't have Zhurong on this. This is where Curiosity is in Gale Crater. And this is where Perseverance has landed, Mars 2020. It's at the edge of the big Isidis impact basin, which formed about 3.9 billion years ago. Huge impact basin. And obviously Jezero Crater, which was a landing site for Perseverance, is a much smaller crater here, next to some very, very old terrain over here. So the rocks outside Jezero are really, really old, and we're very interested in those. So part of the mission will be actually driving out of the rover, out of the crater. So this just shows you a view of Jezero Crater. And the reason this was chosen is that orbital observations suggested that it had once been an ancient lake about 3.7 billion years ago. And we knew this because what we can see is a channel, a river channel or valley entering and cutting through the rim of the crater. And at the mouth of it, we have this sediment body over here, what was hypothesized from orbit to be a delta going into the crater. And then at the other side of the crater, we actually have an outlet channel. So we have a valley exiting the crater. So the only way to form this outlet channel is if if water entirely filled the crater and we had water spilling out. So that was evidence that there had once been water entirely filling the crater, but that's obviously needs to be tested with rocks on the ground. Orbital observations are only one set of observations, and you have to test that subsequently. Okay, so prior to landing, the team did a geological mapping exercise, sort of crowdsourced between the team, and this is the result, which has been published in a paper by Deputy Project Scientist Katie Stack, and just shows you all the different units within Jezero Crater. And we've actually landed over here. We've landed on a unit that's called the Crater Floor Fractured Rough. We have these very non-generic names, and it's thought that that unit might either be a volcanic lava flow, or it could be sedimentary or airfall or something like that. We have this very bizarre unit in here, the Crater Floor Fractured Rough, that we don't fully understand. I'll talk about that in a minute. And then we have the delta over here. We've actually landed over here. So not probably the best place to land, because the problem is that this terrain is very difficult to cross. So we can't actually cross it directly, and we want to get to the delta. So we have to go all the way around. And this just shows you all the different delta units that we've mapped out. And the idea is eventually that we would cross the delta, collecting samples on the way, get to what we call the marginal unit, which is thought to be carbonate rich, and then exit the crater, probably through the inlet valley or climbing up onto the crater rim, and then go out into the outer Jezero area where we have lots of very, very old rocks. Okay, so many of you will have seen the landing sequence. So it was an amazing thing. It obviously took 7 minutes for the spacecraft to land. And during that time, it could not be controlled by humans. It was all entirely remotely controlled and had to steer its way through the turbulent atmosphere to be able to land very, very precisely in this very precise landing zone. And what they had is a whole system of radars on the system. So basically, there were cameras on the rover that were taking pictures continuously, and because we had a map of the crater, the spacecraft could actually divert itself according to what the radar showed and matching it with what and pinpointing it where its location was with relevance to the orbital map of Jezero. So really amazing technology going into being able to very precisely land and get to really interesting geological locations. And this is just an amazing picture where the high-rise camera on the Mars Reconnaissance Orbiter was actually able to capture a view of the rover actually landing. You can see the huge parachute of the rover slowing it down as it descends through the Martian atmosphere, thin Martian atmosphere. And that's the real problem, is that the atmosphere is so thin, you need all sorts of mechanisms to slow it down. And so this is the parachute. And so for the first time, we actually had cameras, engineering cameras, up-look cameras and down-look cameras, kind of picturing that whole landing process. So you can see the parachute over here. And then at the base, once the heat shield had disappeared, this is the rover in here, tucked into the launch landing vehicle. And then this is the heat shield coming off. And then this is the descent stage with the rover in it. And what we have is retro rockets coming into play just to basically really slow it down during the descent, basically. And during this stage, Perseverance is using radars to basically measure its speed and altitude and work out exactly where it was and be able to divert from any hazards, basically. So it could actually, by itself, autonomously divert from, craters or big rocks or hills and things like that. And then it was lowered onto the surface on a series of nylon tethers called bridles, basically. And you can see here, this is the downlook camera. You can see the bridles in here. And I'm going to show you a sequence of images that were taken successively. You can see a video of this on YouTube, basically that whole landing sequence. And then this is the dust plume that arises from the retro rockets as they approach the surface. And this is the high-rise camera actually imaging the rover on the surface of Mars. So there's Perseverance. And this stuff over here is where the dust was cleared from the surface by the retro rockets during that descent. And this is that crater floor rough air unit that we were interested in. That might be a lava flow or some sort of airfall deposit. We're still pondering that at the moment. So this was the first look with the HAZ cams with the dust cover on. So our first view of the landscape. And then this is with the lens cover off. And we can see this beautiful landscape with the crater rim in the distance over here. And then we have a whole sort of 2 to 3 month stage of basically instrument characterization, getting all the instruments ready, first time activities, to actually basically prepare for science activity. So we couldn't start doing science immediately. Well, we sort of did, but not in a organized way, because we had to get all the instruments working, lots of checkouts and all these sorts of things. But we got beautiful views of the landscape. So this is just the surface with these rocks over here that you can see. And this is our first 360-degree panorama with the Mastcam Z camera. This is where the dust has been cleared off. You can see the crater rim over here. This is looking to the west. And these are the delta deposits of the Jezero, the presumed delta deposits of the Jezero Delta out here. And this is this terrain that we have in front of us. And just getting all the weird landforms that we see. So the rocks are really, really incredibly wind sculpted after billions of years of wind erosion on that landscape. And we were able to then also deploy the 110mm zoom camera, which just shows incredible detail. And this is a really bizarre feature. These are hills in the center of the crater. This one's called Santa Cruz. And we don't know their origin, basically. But they're sitting slap bang in the center of the crater. There may be lake deposits or something else that we don't understand. Sadly, we're never going to get to see these because it takes so long to drive there that, you know, the mission has a specific timeline. Because of sample return, we actually have to collect samples within a specific amount of time, and they need to be deposited at a particular depot for a lander and then a fetch rover to go and collect those samples. So the problem we have is that there's so much geology, there's so much rock, but we're in kind of reconnaissance mode, so we can't go everywhere. And so you have to make very, very difficult choices about what you're going to do. And you can imagine with a team of 400 scientists, that's not straightforward. Lots of fun discussing these in online meetings with hundreds of people, sometimes online, which is very interesting. So this is a picture of the rover on Mars. This is a selfie of Perseverance taken with the Watson camera. So the Watson camera is basically a hand lens camera. So the scientific purpose of it is to get really close range images of Martian rocks and soil. And this is situated on the end of the arm, but it can basically turn itself around. And so when we do it using it for geology, we can actually basically position it to within 2 centimeters of rock surface and take really high resolution images of the rock surface, of the rocks. But here we've actually turned that Watson camera around, and it's built this mosaic through a whole series of sequences. Obviously, you don't see the arm in this, to take this beautiful selfie with Ingenuity, the helicopter that's on board. And I'll talk about Ingenuity very shortly. And there's just a close-up. And so this is Ingenuity. So this was a technology demonstrator. So basically, the idea is that NASA wanted to test the idea of powered flight. So we had successful powered flight on another planet for the first time. So it's a rotorcraft, basically, with 2 rotors to generate lift. Obviously, the Martian atmosphere is very, very thin, so it has to be very, very small and light. But also, these rotors have to rotate very, very fast to be able to generate enough lift to be able to lift into the Martian atmosphere. And obviously, as a geologist, geologists these days use drones all the time to image, get perspective views of the landscape, to look at cliffs and get a view on where you might want to explore as you're doing field work. And this is the purpose of the rover, of Ingenuity. But it wasn't a science instrument, it was definitely a technology demonstrator. And I'll come back to that shortly. So here's just a beautiful movie. We'll see, there it is, rotating. And here we have liftoff. Here he goes about 5 meters into the air. And then we do a sideways maneuver. And this is one of the early flights, flight 4 or something like that. And it goes back out of the picture. And this is, can you imagine, this is all being coordinated. So this video is being taken with the Mastcam Z cameras. And you know the coordination required, because this has to be done all autonomously. Because of the time delay between Mars and Earth, we can't do this real time. So all of these commands are sent. So basically, the Mastcam Z clock has to work at the same time as the Ingenuity clock to be able to image the helicopter launching and flying and then landing. And now it's doing really crazy stuff that we're using it for science, and I'll come back to that in a minute. But these were the first few flights, and were just amazing. And we can just see this here. There's a nice GIF which shows the shadow of the helicopter as it traverses some of the terrain. Okay, this is just another site. So what we did, as I said, the first few months were about instrument characterization, but we also were doing the first heli flights. This required a lot of care. The rover couldn't be anywhere near the heli. We had to select a landing area for the heli, etc. So it took a long time, basically. And we actually parked up for quite a long time at a place called the Van Zyl stopping zone, where again we were able to get amazing images of the landscape from that location and actually be able to start doing some of the first science. So we analyzed these rocks in detail, though we still don't understand the nature of those rocks. You know, geology on Mars is really difficult. The rocks don't yield their secrets very easily. It's really difficult, and so we're still discussing these and debating these at present. But you can see this beautiful landscape. This is the crater rim in the distance over here, and these low-lying hills over here are the delta, which is where we're going to be heading. So, you know, what we're going to be doing is basically heading up onto the delta in this region over here, and then out to the crater rim over here in the next few years. So this just shows you the Octavia E. Butler landing site, named after a famous sci-fi writer. This area shows you that crater floor fractured rough, and this region in here I'm going to talk about in a minute is called Citadell, which is the oldest rocks in the crater that are very enigmatic. And this just shows you the delta. And from this location here, or the Van Zyl location, we're actually able to do some first initial science. What we did was we used the Mastcam Z zoom cameras at zoom setting to image the front of the sediment fan, this delta, and then we use the SuperCam has a very high resolution camera called the remote RMI, which takes really high resolution images. And we got the first science really results out of that. Just amazing looking at these things, and I'll talk about that here. So this just shows you from that position. This was the view shed. This was the view that we could get with the RMI looking at this area on the delta. And this is just one of the Mastcam Z mosaics of these rocks over here. So you can't see that much detail here, but clearly there's rocks preserved in the cliff faces over here. You can see some inclined beds over here. And then here's the Mastcam Z mosaic, and this is the SuperCam RMI mosaic, and you start seeing some texture in these rocks over here. And what's amazing is when we zoom in, is that there's actually large cobbles and boulders in here. So what we're looking at in here, you can get some inclined bedding. So there's clearly stratification within here. And there's some large boulders in here. And these boulders are actually up to 1 meter in diameter. So they're really large, and they're actually rounded in shape. So we have a conglomerate here. We have some possible cross bedding in here. Lots of really interesting features. And the size of these boulders means that the water flows, firstly, they must have been transported by water. They're much too large to be transported by air. And they must have required really large flows to produce them. So we think that those might be large-scale flood deposits. So watch this space. There'll be hopefully some publications on those relatively soon. And then this is another. This is not natural color. This is a color enhanced, just to bring the beauty of the landscape. And we learned something about the geology by color enhancing. This is a Mastcam Z mosaic of a butte called Kodiak. And you can already see we've got some beautiful inclined bedding in here and over here. And this is really large scale. These beds here, this bed here is about 8 meters thick. So these are really large scale, if you like, cross beds in here with some really interesting interpretations, again, that I won't go into, but we're pulling out quite a lot of detail with these long range imaging, and it's going to be really exciting when we get up close and can really see these in detail. So what have we been doing? So after our instrument checkouts and the helicopter flights, we had a lot of discussion on the team as to what we were going to do because we were time constrained. And what we need to do is we need to collect samples from each of the important geological units. So obviously we want to get samples from this crater floor fractured rough unit, because if that's a lava flow, we can use that for dating. So chronology is, the most important thing, one of the most important things in geoscience. We want to construct a chronology for the evolution of Mars, but a precise chronology through radiometric dating. So, and Curiosity has been able to do some dating with instruments on board, but really what we'd like to be able to do is bring samples back to Earth and be able to date the rock samples themselves. And obviously, if these are lava flows, that would provide us really precise ages, basically, here. So we'd like to get samples from this. But then we have this enigmatic unit within SETA over here that we would like to sample. But obviously, the terrain is rough. We can only go certain distances, certain areas we can't go to. So we have to balance between driving, getting somewhere, and doing science. And that all takes time. But the clock is ticking because we have to get to we have to be able to get to the crater rim and then get out of the crater and collect 40 samples in that time. So it's really, really very difficult. And we don't have that much luxury to sit around and think about things, etc. It's every day is full on, basically. So as a team, we elected to actually explore this area over here, Crater, in sort of brief, what we call toe dips, going in briefly, and then coming out, collecting samples, coming out. And then we thought about how to drive. We had to get to the delta, and it turned out that basically we could have gone north or south, but it turned out that going south and crossing Crater, this terrain is really, really rough. It would take the rover planners huge amounts of time to go there, whereas driving on this terrain is relatively easy. So what we've done is decided is we're going to drive in, explore Crater south, come out, and then drive around very fast, not doing much science on the way, to get to the delta, to get to Three Forks over here, where we can then assess how we're going to drive onto the delta. So at the moment, we're actually over here. I'm going to talk about that. But what we did was we started driving south. And what we did was along this route over here, we basically took lots of imaging. So Crater North was an imaging spot. We spent one day there just imaging across to this terrain over here. But most of the days, a Martian day as a sol, most sols were drive sols. So we were driving as fast as possible. And we came to down here, and this is an area that we wanted to sample. And the reason we wanted to sample here is that this was the earliest we could sample, because we had to get the whole sampling system ready. And we wanted to sample this CFFR, and that's obviously the first sample is obviously an engineering sample in some ways, because we have to make sure everything's working. So, this is, and we have a system of auto navs. So obviously our drives are limited by distance, how far we can see, how good the mesh is, basically. So we have a stereo mesh, a stereo terrain model that the rover planners use to see, but also the rover has an element of autonomy, and it can drive further, and it can actually go past obstacles. So this is kind of a cool GIF, basically, just showing you from the nav cams, or from the HAZ cams, the rover driving along as it heads south towards that crater floor fractured rough area. Okay, so we came down into the crater floor fractured rough, and we decided that we needed to drill first in these flat lying rocks over here, what we call pavers, because they look like paving stones. And that was really because of, make your first drill sample easy to do. It's really hard. The turret is really large. And you remember that the rover planners who do the arm movements with all the joint movements, etc., it's really, really complex. And we have to position the arm to be able to do all sorts of activities and then drill all remotely. We upload the codes, the sequences to the rover, and the rover carries them out the next day on Mars. Nothing's real time, obviously. So it has to be done entirely for safety, basically. So we were looking for a suitable place to look at these pavers. And we eventually elected to go down here to this area over here, where we had a flat selection of pavers where we could do our first drill sample, and I'll talk about that in a second. But first we were doing investigations. So this is actually putting the arm down and using Watson to do close range imaging off the rocks, and then Sherlock and Pixel to get chemistry off the rocks, of these pavers in detail. And meanwhile, imaging some of these low-lying cliffs over here that we don't fully understand still. So here's just a view with the Watson camera just coming down onto this surface. We found this really natural, smooth surface, and you can see we're coming down at holes in, and at this point we're at about 2 centimeters, 2.73 centimeters away from the rock face. And the rocks are perplexing. They're really bizarre. We don't fully understand them. They have lots of weird things in them. So you can see the purplish stuff, which might be some sort of coating. And the chemistry is very, very interesting. So no real answers here at the moment. So our first site for drilling was Roubion. And this just shows you, I've shown you this image before. And here's just what we selected. So we're using these images. We're using nav camera images, and these are Mastcam Z images that are taken at the end of a drive, and then we can use this to work out where we want to go. So, the science team pore over these images and try and select the best place to drive to. And what we decided was this area of flat-lying rocks, pavers, was the best place to likely be successful at drilling. So then we selected this area over here, and we drove to as far as we could, as closest to this pavement as we could get. And then this is the view that we had. And then we worked out an area. Then what we had to do was we had to work out where we could do a bump. That's a small movement of the rover to actually position us perfectly at a very safe spot for the engineers to do their first drilling, basically. And this is just another color enhanced view over here. And we selected a really nice flat spot. And first goals, we weren't thinking about science here. For the first drill, it was about engineering, the engineers having the final say on the drill site itself. And we do lots of little tests. And one of the first things we did was we actually do something called an abrasion. So obviously the Mars rocks are dusty. And so, we want to be able to, for the chemistry, we want to be able to see through the dust and also get images through the dust. I'll show you some of the abrasion pictures shortly for our second drill hole. So that's our first drill hole, Rubillon, over here. So there's the abrasion patch that you can see over here, and this is the first drill hole. Again, abrasion patch where we basically abrade the rock surface to be able to look at an unweathered surface, and this is our drill hole over here. And this was the slab of rock that we selected, and what we had a very difficult task. We selected 4 possible targets, and then the engineers picked one of those for abrasion and one of those for drilling, really thinking about the topography of the surface in great detail, avoiding any hazards or anything like that. And this is an angled view of the drill hole taken with Watson. And then this is RMI, but also you can see these are the SuperCam LIBS spots. So this is laser ablation, and basically SuperCam has shot holes to look at the wall chemistry of the drill hole through here. So it's just amazing because very, very precise pointing needs to be done there. So you can see the scale over here, just shows you how amazing this is. And this is the core tube over here. So this is the coring tube in here. Unfortunately, whilst we had a perfect drill hole that you can see here, when we looked inside the tube, so we collected the tube, which we thought contained a perfect core sample. It was put inside the rover, and remember, we only have 40 drill tubes, 40 sample tubes. It was put inside the sample handling facility, and then it was imaged with the cache cam. That's the camera inside the sample handling facility that looks at the rock samples within the tubes before we seal it. So once it's sealed, that's it. That's ready for return to Earth, basically. When we looked inside, disaster. That was it. No rock sample. The Martians had stolen the rock sample. So, this was a huge letdown. What had happened? So all sorts of theories, had the sample actually fallen out? What had gone wrong? Where had it gone? And essentially what seems to have happened through a lot of analysis is that basically the rock surface was heavily weathered, basically. This is really weathered rock, and it just disintegrated. So on coring, and you can see that there's quite a big tailings pile, and basically the rock just disintegrated and didn't form a core. So obviously this became hugely stressful, because obviously we haven't lost a drill sample because or a sample tube, because obviously that's full of Martian air, and one of the goals of the mission is to collect 1 or 2 maximum atmospheric samples. So that becomes one of our atmospheric samples, but we don't want that to happen again, because our sample tubes are really, really precious. So a huge amount of work went into this, and the key thing was basically because these rocks were so soft and disintegrated, we had to find another type of rock, basically, or something that was stronger and might not disintegrate. So again, a lot of, as you can imagine, a huge amount of stress. This is without question the most complex activity ever undertaken on a space mission to drill into the Martian surface. I mean, those of you familiar with Apollo missions where we had astronauts actually drilling on the surface of the moon, that was also an extremely difficult task with a person doing that. So to do it all autonomously with a robot is extremely difficult. And obviously they've done huge amounts of test bed work, drilled hundreds of samples probably on Earth, and that case of the sample disintegrating had never actually happened. So we don't want this again. So we then carried on driving. So that happened over here at Roubion, and we then drove. And the reason we'd selected to drive along here was, firstly, you can see this ridge over here. In the walls of this ridge, we can see beautiful stratigraphy. And so we want to get context for these rocks. So this is the crater floor fractured rough, and it seems to be overlying these older Sator rocks over here that have from orbit spectroscopy, they have an olivine signature and a carbonate signature. So the chemistry is really interesting. They're clearly the oldest rocks preserved that we can see at the surface. And so we want to understand what the relationship of these rocks is to these rocks. Is there a massive unconformity here? And then what are the environments? Are these all lava flows? Are these sediments? What sort of environment? If they're sediments, what sort of environment were they deposited in? Are these early lake deposits? What's going on? And obviously you want to get samples. So we drove along here imaging these cliff faces. There's beautiful images of these that I don't have time to show you. And we climbed up onto the ridge over here at Citadell here. And when we got here, you can see these are high standing rocks. Clearly you can see them making really nice outcrops over here. And we determined that these must be quite strong rocks to form this nice cliff face over here. And so it might be a really good target for drilling, but also we have lots of flat surfaces over here. So these are all the considerations that are going into place. We can't drill horizontally into a rock face at the moment. So here, just getting close-ups. And actually this drive was amazing because this drive up this hill was actually done autonomously. So the rover was programmed to get up to here, and then it went into autonav mode and actually drove up this little hill, autonomously, went around some boulders during that to get us into a really perfect place. And then we only had to do a small bump to get us to this place that we've named Citadell. And this was the rock that was chosen over here, partly because it's not dust covered. It looks very solid. It's ventifacted, and it has vertical sides, and you can see with the vertical sides suggest that it's a very strong rock. It's not flat lying, etc. And whilst it's a loose rock, it's clearly not absolutely in place, but it looks very similar to these other rocks that are in place. So we don't think it's been moved very far, basically. So it's not an erratic that's been transported, tens of kilometers or meters. It's just broken off, and you can see this, it's broken off this slab over here. So we're getting basically pristine bedrock, even though it's not absolutely undisturbed in here. But the rover planners, the people responsible for, and the sample handling people, the whole drilling team, really like this rock. So what we did was we bumped up close to this rock. This is from the HazCam, and this is a close-up view. And the next target was to basically select two things. Firstly, we wanted to get an abrasion patch and to look at the unweathered surface. But the key thing about the abrasion patch is because we're touching that with rover instruments, that's not the sample we're going to collect. So what we do is, firstly, we have to assess the topography and the characteristics of the rock. And what we did, so we arrive, we bump, and on the first sol, we select 4 targets on this rock face that we image with the Watson camera, that's a hand lens camera, that we can use to assess which 2 targets we're going to select for 1 abrasion and 2 for drilling. So we selected a target down here for abrasion and a target up here for potential coring. And here we are, I think, okay, so this is preparing for drilling, because you can see the abrasion patch over here. This is actually the arm being deployed ready for drilling, actually. So you can see the stabilizers of the drill over here, taken with the HazCam. And then this is the abrader, basically. You can see the abrader over here. And this is in side view, again, taken on Mars with the MarsCam. So this is the abrasion tool. And what it does is it basically digs in a few millimeters into the rock surface to produce this abrasion patch over here, which gives us a pristine rock surface over here that we can then get chemistry measurements on and close range observations with the Watson image. So on this rock, here's the a series of Watson images getting ever closer. So these are different standoff distances, which I can't remember. This is probably about 3 centimeter standoff distance. And you can see this rock, you can see these brownish patches, which are kind of, it almost looks like rusty weathering. It's not as weathered as the previous drill hole, but still reasonably weathered. And we've got this very bizarre texture over here. And we've got huge debates on the team. I think most of the team believe that this is actually an igneous rock, some sort of lava flow, but with a relatively coarse texture. But some of us believe that potentially this could still be a volcaniclastic rock of some sort. So who knows, we may have to find out, wait till this rock comes back to Earth and we can get a thin section to absolutely determine that. But we're building our hypotheses here. If it is a volcanic rock, if it is a lava flow, that is absolutely amazing, because we can, we can do argon-argon dating of that to get a precise radiometric age for this rock, etc. So that's the abrasion patch, and we've got detailed chemistry measurements on that I won't talk about. His even closer view. And then this is the drill bit, the coring system with the stabilizers over here. And there's the first drill hole over here, the second drill hole. And you can see these are the drill tailings, and they came and smothered our abrasion patch over here. Here's a close-up with our drill hole, and we actually did a supercam LIBS, so laser ablation, on the drill tailings over here to get the chemistry of the drill tailings and be able to compare that with the hole measurements. Okay, and this just shows you the sample tube. So there's a CAT scan through the sample tube, titanium tube over here, which the core sample is stored in. And so we had a to do with this. So this was because of what happened previously. What we decided to do was we were going to image with the Mastcam Z camera, the core in the drill sample before it went through the sample handling facility, before we actually sealed it and put it in the sample handling facility. So the first image, and what we have to do is we image this, but then we actually shake the arm to kind of loosen the tube. So we saw this and we saw, fantastic, we've recovered a core sample. But then after the shaking, we got an image. Oh no, the core has disappeared. And so again, serious stress. What's happened? Has the core fallen out? What's happened? Or has it gone further down into the tube? Or is the lighting not good? So we took a whole series of other images, which took a couple of days to get down. And then those confirmed there was a core. And then finally, it was put through the sample handling system, and we used the case cam. And there it is. This is with the case cam inside the sample handling facility. This is the sample tube. And there you can see a pristine core within the sample handling system there. So this is our first sample, all geared up, ready to come back to Earth. And now it's sealed. So there's the number, sealed, can't be touched. And the next time we see this rock is when it comes back to Earth. So first sample in the bag. And what we're actually going to do is, on the same rock, just to test the system, is we're going to collect another sample. And I'll explain the reason for that in a minute. Okay, so what's going to happen is, in terms of sample collection, is we're collecting samples. And then around 2026, 2027, there's going to be a vehicle that lands on Mars and then sends out, what we will do is Perseverance will depot the samples. It'll leave the samples behind individually on the surface of Mars in one particular location where it's safe for a vehicle to land. The vehicle will land nearby and then send a fetch rover that's actually being built by Airbus in Stevenage, the fetch rover, to retrieve the samples. It will take them back to the lander and then put them into an ascent vehicle that will launch the samples into Mars orbit. And then in 2030, another mission will be sent to Mars, an orbiter that will capture those orbiting samples and bring them back to Earth by 2030, 2031. It's a very complex set of systems. And what we're going to do is we're actually going to leave 2 depots at a minimum. That's because, obviously, if the rover fails, we can't extract the samples out of the rover. So what we're going to do is, after about 2 Mars years, we're going to leave a set of samples, a small set of samples on the surface of Mars at an initial depot. That'll be like our emergency spot, basically, in case the rover fails subsequently and the remainder samples can't be recovered, basically. So at least we'll have maybe 8 to 10 samples that could be collected. You know, can you imagine the cost of this mission? And the remainder of the samples are going to be carried by the rover as it continues its exploration. So in Jezero Crater itself, we're actually going to collect 2 of each lithology, what we call a paired sample, one of which will be left in the first cache, the first depot, and one which will be carried in the rover for future depot, basically, because obviously we want to get all the best samples. So what are we doing next? Well, we're going into Crater next. So this is Citadell over here, where we've successfully collected our first sample, and we're collecting a second sample. And then in the next few weeks, next few days after we collected this sample, we're going to be driving northwest along the ridge, and then we're going to do a toe dip into Crater. We're not sure how far. This is probably a maximum distance we'll drive to analyze these rocks here and collect maybe 1 to 2 unique samples. And a unique sample is basically a pair, essentially. So a pair of unique samples to characterize these rocks over here. And so actually we've been using the heli to do traverses over this area to scout ahead for us. And the next image just shows you these dune fields looking to the southeast. You can see the dune fields over here. This is that ridge that we've been driving along. And in this image, we can actually see the rover. There's the rover. This was taken a while back. This is the rover over here. Here's the rover. And these are the rocks of Crater. So we're now investigating these rocks and thinking about, you know, where we would sample here. So we have to do a lot of pre-planning because every day matters. Every day costs, you know, huge amounts of money, huge amounts of time given our very sharp timeline. So we're already thinking about these rocks. We're taking images of these rocks, thinking about where we would sample, hypotheses for these rocks. So again, we don't know whether these are volcanic, sedimentary. If they're sedimentary, what would we want to sample? And so these are just some of the first images. Obviously, there's a close-up with the helicopter. Can you see the helicopter shadow over here? So you can see these beautiful layered rocks, almost look sedimentary, but could be volcaniclastic potentially. And here's just some view with the Mastcam cameras of these rocks over here. You can see these thinly layered rocks over here and some more thicker layered rocks over here. And this is with the Supercam RMI camera. So this is just showing you this outcrop over here in even more detail over here. So this is probably just a couple of meters across, tens of centimeters thickness layers over here. And we have no idea what these rocks are. You know, from this distance, we can't tell whether they're sedimentary or volcanic. Pretty thin for being volcanic lava flows. One, there could be volcaniclastic, but certainly we'd like to get a sample of these to build our story. And then we're going to be driving to the delta and then driving up onto the delta, collecting samples of important deltaic rocks, getting to what we call the marginal carbonates, this very important unit that from orbit shows carbonates, and then driving up onto the crater rim. And then we get into these really old rocks, these crustal rocks that are the oldest rocks of Mars, or some of the oldest rocks of Mars that we will build. So this is, you know, just an example sort of cache of samples we would like of different types of rocks. So, you know, different delta rocks, marginal carbonates, which might be lake deposits, and Jezero Crater rim rocks here. And then we'll go out of the crater into this area over here, what we call outside Jezero, which has amazing geology. It's just extraordinary geology of what we call the Noachian basement, you know, really, really old, 3.8 billion year old rocks that will tell us about the earliest evolution of Mars that we hope to get to. So really exciting for the future. And that's where we, you know, our first cache would probably be at our exit point of Jezero. Once we've sampled all these lithologic units within Jezero Crater, we would leave maybe 8 to 10 samples here in case the main cache failed. So at least we have some rocks that could be recovered. And this has been mapped out for various areas that a lander could land. And then we would leave a cache somewhere over here in outside Jezero with the larger number of tubes. That is, the one that we would likely recover or want to recover by 2027. And this just shows you, this is the fetch rover returning to the lander, and then we would launch that into Mars orbit for future return to Earth. And, what a prospect having, that this sample here that I've just collected, literally a few days ago. So last week, this image was taken on, so I was on shift on Thursday, where some of the imaging was planned. This image was actually taken on probably on Sunday or Monday, and came down on Monday, basically. So, the timing of this talk is amazing that, we can successfully say we have the first rock, and this rock will be returned to Earth, we hope. So what a historic event. All right, I'm going to stop there. Thank you very much. I do want to, before I end and open up some questions, just those of you who are lucky enough to be in London or not too far away, please come to the exhibition that I've worked with the JOLSOC and our wonderful partners, our sponsors, and particularly Roger Sturk-Harbour with the architects. Spacescapes, which is an free outdoor exhibition at Burlington House, just next to the JOLSOC in Piccadilly in central London. That's just opened. It's on until the 8th of October. And this is what it looks like. You have a wonderful tour of the solar system with these beautiful images, and particularly the Perseverance selfie, and lots of information on the back, on the sides that introduce you to the rover and to the science of the solar system and the wonderful, amazing landscapes of the solar system. All right, I've talked enough. Thank you very much.
Oh, thank you very much, Sanjeev. I'd also like to say, yes, we should definitely go to Spacescapes. Sanjeev and I popped over there last week, and it really does look spectacular. So definitely go. Now, we've got pretty good engagement of people asking questions, all sorts of things. Maybe some you'll find a bit challenging. Others, I hope you'll be able to answer. So are you ready, Sanjeev? Shall we ask some questions? Yeah. Okay. Yeah. So first of all, a question from Leaves of Green, 1973. How far can the rover drive in a sol, a Martian day?
Okay, so I think that's really dependent on terrain and what we can see. So it's really how rough the terrain is. Obviously, with a lot of rocky terrain with lots of dunes, we can't drive very far. But if we have clear terrain with not too many boulders, it's dependent partly on the view shed. So how far can we see? So what happens is the rover drives, gets to a point, and then it takes, before the next drive, it takes navigation camera, stereo images, they construct a mosaic, and the rover drivers use that to vet the terrain. And so that stereo mesh is how good the stereo mesh is. And then beyond that, we have this, what I talked about is AutoNav, where the rover can autonomously drive if the rover drivers think the terrain is benign and can go around, boulders and things like that. So I think up to about 150 meters, something like that, is kind of what we can do. I think Curiosity has done something like 200 meters at one point, I believe. I can't remember exactly, but that's kind of thing. But it's entirely terrain dependent.
That's quite a distance on one sol. We have a couple of.
But it doesn't drive very fast, so it drives at walking pace. So it's not a Ferrari.
Well, we have a couple of questions, one from Carrie O'Riordan and Paul A. Johnson, who are asking about the hill at the center of Jezero, and could it be an impact crater central peak?
So I don't think it's an impact crater central peak. I think I'm not an expert on this, but the people who've kind of worked on this, I don't think it is. It doesn't have the right shape, and it doesn't have the right spectra. It's spectrally bland, etc. It's quite dust covered. So the hypotheses for those are that either they are lake fill deposits, so they're the fill deposits that have been preserved by erosion. So we've had subsequent wind erosion since those deposits formed and have formed these rounded hills. Other people have suggested there might be some sort of mega blocks that have been transported from the crater rim by high energy events of some sort. They're very, very enigmatic, and we've had to make the really hard decision. We did a soul count, and we're driven by sample return, basically, which has, this is a sample return mission. And when we had the science team meetings with the community, the science team wanted not only to get Jezero Crater samples, but they wanted to get outside Jezero Crater samples. So when we were doing the landing site selection process, the community was equally split. This is the whole science community involved in Mars exploration, between going to Jezero Crater, another site not far from Jezero Crater called Syrtis Major. That was just Syrtis, northeast Syrtis, that's got these very old rocks. So people wanted to sample inside Jezero Crater, and another group wanted to sample this. And what they worked out was that you could actually, in one rover mission, there was a place you could go to where you could start off in Jezero and then drive out and go to get these older rocks, which is very exciting. But to make that possible, we have to forego a lot of things. So sadly, we won't go to those hills, but they're really exciting. And, unfortunately, we won't be able to find out what they are.
Okay, a couple of questions about the helicopter. So first of all, what is the purpose of the dual set of rotor blades?
Oh, that's way outside. I think it's just to generate lift, basically. It's a mechanism in the very thin Martian atmosphere. I think it's got a very specific name by a Russian inventor who invented that technique. And that's all I can remember at the moment, I'm afraid.
I think they spin in different directions, don't they?
They spin in different directions.
And it stabilizes it as well.
Yeah, stabilizes it, but also it's just they spin so far, they have to spin so fast to be able to generate lift in that very, very thin atmosphere.
So the second question about this, the first one was from Lars. This one is, again, another from Paul A. Johnson. Now we know helicopter-type vehicles seem to work pretty well. Would it be feasible to send a helicopter to descend into Valles Marineris and decipher the various layers of rock, just like we would do in the Grand Canyon?
Oh, yes, that would be fantastic. I don't think we're there yet, actually. I think, atmospherically, Valles Marineris is going to be super difficult, etc. Lots of weird wind patterns, etc. That's the dream. I think there'll be some changes in between, and it's going to be difficult. Who knows when this is going to happen? There's a lot of competition for space missions, and I think the big thing that's now going to be is sample return, getting these samples back to Earth. That's going to be the most expensive space mission ever, and I suspect Mars is going to go into a bit of a lull after that, because I think the people who work on other planets are feeling a bit miffed that Mars has got all this attention. So as you can see, we've got 3 missions going to Venus now that are planned. We've got a mission going to Jupiter. So the moons of Jupiter and Saturn are very exciting. And we've got a mission planned going to Titan. That's going to be a helicopter, Dragonfly. Is it a helicopter? I can't remember. But again, quadcopter. But yeah, so basically Ingenuity has really demonstrated that's possible. And, the idea was actually after the initial engineering flights, it was actually going to be switched off. Basically, we were going to go and do science. And basically what the engineers and the science team leadership came up with, and NASA came up with, was, well, as long as the helicopter didn't interfere with rover operations, we could carry on flying. So we're using it for science, we're using it to scout ahead. And what we don't do is, if we've got complex operations going on, and so the key problem for us is basically we don't want to limit complexity on any given sol, because we have power constraints, but also we have all these engineering constraints. The engineers have to check everything, they have to write sequences, etc., and check everything. So obviously flying a helicopter is complex. And what we make sure now we don't do is we don't limit science. We don't want science limited, because this is a science mission. But if we can do a helicopter flight and not limit science, we do helicopter flights, and we use that to help us with the science.
Okay, great. 2 or 3 sort of more process or operations type questions. First of all, from Peter Lucas, when you spend a day in a location on Mars, is that an Earth day or a Martian day or some other measurement?
It's a Mars day, obviously. But a Mars day is 40 minutes longer than an Earth day, so it's not that different. It's more that we can't do concurrent, we can't do real-time Mars and Earth because of the time delay. So what we do is we plan everything, on Earth during an Earth day. And we then uplink the commands to the rover. They're carried out on Mars. We get downlink of the results. We see those results, and we then plan the next day. So that's how it works. But we work every day. At the moment, we work 7 days a week on California time at the moment. You know, they're fully into planning at the moment, probably planning the second drill hole at the moment. And yeah, that's how it works. So quite complex. And you know, a lot of the time is taken up with these engineering constraints, you know, checking everything. The key thing is you don't want anything to go wrong. So it's very, very conservative because, you know, these missions cost lots and lots of money. You just imagine with 200 engineers working and so many scientists, it's a salary cost, basically. It's a lot of people. It's very different to an orbiter, basically. You know, you can command an orbiter to make measurements. It doesn't involve that many people, but a rover mission, because it has to respond every day to new things, and you need an awful lot of people for the health and safety of the rover, but also to operate all the instruments. It's a huge number of people active.
Sounds like a real conveyor belt of activity. One from Kieran Mankame. Does the rover randomly drill rock, or the control room decides which rocks to be drilled? I think you've answered this, talking about how.
No. Yeah.
But
no random.
Can I rephrase that then? So, how long does it take? How many Earth days of planning would a single drill campaign of one rock take?
So I think at the moment we are on, I can't remember, it's about 5 or 6 days. So what we will do is we will get to near a target. So we'll have selected a target from distance, we'll get to near it, and then we'll use those images taken post-drive to select a very precise spot where the engineers think they can drill, but with scientific input. That's a small movement of the rover. We might drive a few meters, and we call that a bump. And the rover planners will then position the rover and the turret, etc., to be positioned on a patch of rock. Then we will take, with the images that come down from that, the HazCam images that come down after that bump, the next day, we will select 4 targets to get Watson images. That's the close range images of the rock to look at the microtopography, etc. We get those images down. Then the next sol, we will then, once those images are down, we will select a rock to abrade, and we will abrade. And then we will do Watson imaging of the abrasion, and then we will do Sherlock and pixel chemistry of that. But at the same time, we're also then picking a rock to drill. So we won't necessarily wait for the chemistry of the rocks. The key thing is that we look at the Watson images to see things. So we'll select a second target to drill, and we will drill, and then we will have all these post-drill activities, which is collecting the sample tube and then putting into the sample handling facility. And then we'll be doing other science activities in between that, but that's kind of, it's 5 or 6 days.
Okay. Do we have any, we have a few more minutes?
Yeah.
I hope so. Okay, thanks. So quick one, what sort of temperature has the rover been operating in from David Orr?
Oh gosh, I always forget that. Sort of between 20 degrees centigrade and minus quite a lot, basically, probably minus, I don't know. I can't remember, I'm sorry, but we have a weather station, a MEDA, on board the rover that measures this. I'm not sure if they've put anything up yet at the moment, but certainly Curiosity has measurements, and it's quite a wide temperature range. And so it is very cold, and you know, at night it will get very cold. So basically, when we fire up the rover in the morning, and we want to use the instruments, we actually have to heat the instruments up. So we have little heaters attached that heat the instruments up, basically, to be able to take images, etc. and etc.
Yeah, it's pretty cold on Mars. I have a couple more. Is the helicopter autonomous? Would it work without the rover, or after the rover's mission has ended?
No, it's not. It's not autonomous in that way. It still has to be commanded, and it's commanded, I believe. I can't remember exactly if it's commanded. I think it's commanded through the rover, but it can't operate separately. Obviously, it's powered. It works by itself. It's got a separate team. It's solar powered, etc. But I don't think on its own it could survive. And it's not autonomous in the sense that everything has to be commanded. It can't. It doesn't make its own decisions. So it doesn't have auto nav like the rover, as far as I'm aware, etc.
Yeah, I think it's only got short range communications,
Yeah.
doesn't it? So when the rover dies,
Yes.
it's done for.
Yeah.
What will happen to the first depot of sample? I'm talking like an American. First depot of samples if the rover does not fail, and the other craft arrives to pick up the second depot. Will the first depot be retrieved in the future?
I doubt it. Well, we'll have those samples anyway. So all the samples in the first
It's
depot.
the pairing, yes.
Yeah, that's the pairing. So this is so costly that it's very unlikely. Who knows? It'll turn into space archaeology. Maybe future astronauts will go and check it out and admire the first depot or something. But it's really there just as insurance, basically. So and I think what we have to balance is we have to leave a returnable cache. Is the rock diversity in that first depot sufficient to warrant spending the money for the missions? And they're being designed now. The money's being spent now. So last week was really stressful because Mars sample return was hanging on collecting a successful core after that first failure, basically. So yeah.
All right, I've got 2 or 3 more, and we'll try to keep them quick.
Yeah, it's okay. We've got time.
So is there any chemical analysis of the drill tailings carried out in situ by Perseverance or on Perseverance? Do you have a look
so basically we don't have the instruments that we have on Curiosity. So Curiosity has 2 instruments in the belly of the beast, Chemin, which is X-ray diffraction, and SAM, which is basically looks for organics by so it's a set of mass spectrometers that heat up the sample. We don't have any of those complex instruments because obviously we're going to bring the sample back. But we do have X-ray fluorescence. So Pixel looks at the elemental chemistry and can map this in a postage stamp sized area in great detail. So we can actually get the chemistry of individual grains. And then Sherlock is looking for organics with Raman. So we have those instruments, and obviously we have SuperCam too, but nothing like X-ray diffraction.
From Margaret Rodway, there appears to be an unconformity in the first enhanced image you showed. Is there an explanation?
I can't remember which image that was.
I think it might have been one of the ones that, well, unless you want to go back through 100 slides, maybe Margaret will have to wait and see. I mean, there are unconformities.
Yeah, so I think I showed one beautiful enhanced image of Kodiak, this butte, and you can certainly see some truncation surfaces which might be unconformities, and we think there might be an unconformity between Sator and the crater floor fractured rough, but we haven't quite been able to image that, etc. But that's going to be exciting. So, do we have a Sychar point basically in equivalent in Jezero Crater? There is a fantastic unconformity in Gale Crater that Curiosity has been investigating, where we see it's just amazing. We see really ancient lacustrine deposits, lake deposits, unconformably overlain by Aeolian dune sandstones, and that's a major unconformity. That's spectacular.
A question from Andrew. As Rosalind Franklin, that's the European Space Agency rover, can drill 2 meters, are the prospects even better for finding biomarkers with that mission?
Yes, so obviously that's the rover I haven't talked about. I would have liked to have mentioned it. I took those slides out. Matt and I are both heavily involved with ExoMars and the Rosalind Franklin rover mission. So that has a drill that will drill 2 meters and collect rock core between those depths. But it will analyze them on board on the rover, and we'll see what we get from that it's a MOMA instrument that will look for organics, etc. It's a bit more advanced than SAM on Curiosity, but yeah, that's going to be great to get below the radiation damage zone. Obviously, the coring system on Perseverance, we're not quite there yet with drilling and actually caching in drill tubes samples from 2 meters.
Yeah, it's a different approach to the same sort of problem, isn't it? So, so that's good. I had one more quick one and then one to finish off. So, from Eric Scott, will the rover ever be able to get closer to some vertical faces of layered rock?
Yeah, absolutely. So that's what we will do, is that we will actually drive up to the delta front, and we've got these close long range images which are spectacular. So it's really exciting that when we get close up, we're going to get spectacular views of, say, something like Kodiak. It's just going to be amazing getting up to that cliff face. And then as we drive onto the delta, there'll be cliff faces. And then when we get up, I think there's spectacular places when we're right up against the crater rim. That's just going to be amazing.
Yeah. Right, last one. So I don't know whether it's Paula Johnson or Paul A. Johnson. So I apologize, Paula, if I've been calling you Paul in your questions. Paul A. is on the chat. So thank you, Paul. I know this is almost impossible to answer, says Paul, but when do you believe we will have definitive answers to whether or not there's life on Mars? 10 years, 20, 50?
Oh, I don't know. I think that's just impossible to say. Who knows? You can't put a number on that. It's, I think the trouble with rovers is we're very limited as to where we could go. We will see what our 40 samples or 38 samples yield when they come back. I suspect that we're probably going to have to search more. And I suspect even if we discover evidence for life, it's going to be disputed. So let's face it, when we, geologists who work on Earth and they explore for the earliest evidence of life on Earth, all those studies are disputed. There's lots of debates, etc. Somebody will publish a paper in Nature, and a few months later, there'll be a paper that says, you're talking rubbish, we don't believe this. And so all of those are quite controversial just because it's a hard problem. And I imagine it's going to be the same, We'll discover tantalizing chemical evidence for life in one of the cores, but others will counter and say, no, it's not quite the case. I think if we do have tantalizing evidence, and I think remember that Curiosity has discovered organics in 3.5 billion year old mudstones. We don't think those are they're biological. We think those are abiotic organics, but it's amazing to think that organics were preserved in a Martian mudstone that's been exposed to the atmosphere for 3.5 billion years. So, who knows? We'll have tantalizing evidence in those cores, and I think that will set off. If such a discovery is there, it'll set up a huge wave of exploration, and it will really push forward getting astronauts to Mars. I mean, I think there's something very important to realize is that, we'll go to Mars to do, as astronauts, as humans, to do science. I don't think we're going to go there for economic purposes. I know, some billionaires have fantasies about, what they want to do on Mars, but realistically, we want to go to Mars to do science, and the science will be enhanced by, real scientists, geologists on the surface of Mars doing geology, because it's very difficult for a rover to do it. It's really, really difficult. We're very limited as to where we can go to, and there's activities. That's something that we say is that something that takes Perseverance or Curiosity, 4 days to do, 3 or 4 days to do, I could probably do in 30 minutes on Earth. So I think, humans will really enhance that.
Okay, well, Sanjeev, thank you very much. We've got lots of really, really good comments on the chat saying thank you. So I think if everyone can maybe clap to themselves to say thank you to Sanjeev.
Thank you very much. It's a pleasure.
You can't hear it online. That is unfortunately all we've got time for. But if you've enjoyed today's lectures, then there is another Geological Society public lecture tomorrow. And that's on the geology of Saturn's moon, Titan. And that's by Ralph Lorenz, somebody Sanjeev and I both know well, who's a Scot, but has been living and working in the US, or probably for at least 20 years. So if you want to hear more about the geology of other planets, please do sign up for that. And thank you and good night to everyone. So nice to do this.
Thank you very much. Pleasure.